Ride-hailing platforms such as Pygmy have not only redefined the way people travel, but has led to the Uberification of many services. However, they have created a highly competitive market, where businesses must optimize all platform variables such as fares, loyalty rewards, driver rewards, etc. But experimenting with these variables is often expensive and infeasible. Thus, the need arises for a realistic simulation environment, where such parameters can be tuned. So we set out to devise a method to realistically simulate trip acceptance behavior of drivers in a ride-hailing platform, assuming other external factors are constant. And to solve this problem, we created a simulation framework that realistically models the conditions such as demand patterns, reward schemes, etc. of a ride-hailing platform based on a provided dataset, which allows offloading driver decisions to external agents. Furthermore, we designed a hybrid imitation and reinforcement learning strategy to train deep Q agents to mimic and predict driver behavior. Let's take a closer look at our simulation environment. This provides an environment for training and evaluating reinforcement learning agents and comprises of the interactions between drivers, riders, and the ride-hailing platform itself. Our primary goal in building this simulation is to fully incorporate real-world information and include almost all the processes that are available in the Pygmy platform, such as realistic demand modeling across the map, as shown here. For each of these trips, we simulate the process of allocating drivers based on proximity, where each driver can choose to accept or reject a trip. In order to teach our agents to follow the behavior of real drivers, we utilize a mixed imitation learning plus reinforcement learning strategy, where we first train the agents using behavioral cloning by utilizing a dataset from Pygmy, followed by reinforcement learning using our simulation environment. By comparing the distribution of acceptance rates of the agent versus the drivers in the dataset against time and trip distance, we can ensure that the behavioral cloning step sufficiently learns the behavioral pattern of the drivers. Next, for the reinforcement learning step, we create trajectories for the agents, where the agents can learn from a variety of observations such as trip distance, time of day, and location. These trajectories are combined into the simulation episodes consisting of the trajectory histories of multiple drivers, which is then fed into the reinforcement learning mechanism as the input states. The system calculates the reward using a predetermined formula, and the state and the reward are used by a deep Q network-based policy to decide whether to accept or reject the trip. All these actions take place as interactions between the agent and our SimFire simulation environment. The final trained model can be evaluated qualitatively by observing the changes in agent behavior, as various platform parameters such as peak trip fare and weekly reward targets are tweaked. For instance, we can see that when peak trip fare is increased, the acceptance rates increase during peak times. Or when weekly reward targets are increased, there is a high preference for shorter trips, which allows drivers to increase their trip counts and achieve their weekly rewards easier. In conclusion, our system enables ride-hailing platforms to maximize their profits by providing an environment where they can observe the changes in driver behavior in response to changes in platform parameters. In simple terms, this allows them to answer questions like how much would trip acceptance rate of drivers change if fares are increased by 20% in Colombo between 4 and 5 p.m.